Hi, everybody. Now we're going to section 1.2, and that's the definition of divisibility. A lot of the things that we're doing here are things that you've seen a billion times, but we're giving more, I don't know, precise definitions and to work with them in somewhat different ways. So let's start right away. An integer a is said to be divisible by an integer b if there exists an integer c such that a is equal to b times c. So a is divisible by b if there is such an integer c. And it is clear that a is also divisible by c. For the same reason. Now the integers b and c are said to be the divisors or factors of a. So if a is equal to bc, b and c are divisors of a, or you could say b and c are factors of a. Further, we say that a is a multiple of b, or a is a multiple of c. These are all different ways of saying the same thing. And the process of finding two integers b and c, such that bc is equal to a given integer a, is called the process of resolving a into factors, or factoring a. And that's something we've done many, many, many times. To factor a number, to factor a polynomial, we've done factoring many times. And a is said to be resolved into factors or to be factored. Okay, now we have some very fundamental theorems right here. Let's start with number one. If b is a divisor of a and c is a divisor of b, then c is a divisor of a. And it's kind of like a transitivity type thing. So how do we show that? Since b is a divisor of a, then that means there exists an integer beta such that a is equal to b times beta. And since c is the divisor of b, there's an integer gamma such that b is equal to c gamma. Well, if you substitute this b into that equation right there, you get a is equal to b gamma, which means a is equal to c gamma beta. Well, that means c is a factor of a, which is really what we're trying to show. C is a divisor of a, as was to be proved. Next, if c is a divisor of both a and b, then c is a divisor of the sum of a and b. And we can show that in a very similar way by premise. A is equal to c with a alpha, and b is equal to c beta. Right, because c is the divisor of both a and b. Well, if I add a plus b is equal to c alpha plus c beta, which is c times alpha plus beta, which is c times, I'm just going to take alpha plus beta and call it delta. It's just c delta. So see that a plus b, we see that c is the divisor of a plus b, which is what we're trying to prove. And number three, if c is a divisor of both a and b, then c is a divisor of the difference of a and b. And that proof is the same proof. Instead of having a plus there, you have a minus there. Otherwise, it's the same thing. That's a minus, same thing. Okay, let's define a few things here. We have a whole bunch of little definitions here. Let's get them right in. If a and b are both divisible by c, then c is said to be a common divisor or a common factor of a and b. Every two integers have the common factor 1, because 1 is a factor of everything, 1 goes with everything. And the greatest integer which divides both a and b is called the greatest common divisor of a and b. And sometimes they call it GCF, GCD, same thing. F would be factor, D for divisor, but the same idea. More generally, we define in a similar way a common divisor to be the greatest common divisor of n integers, A1, A2, AN. So this could be A1 is a number, A2 is a number, AN. So you have n numbers here, and whatever the greatest common divisor of all of them is, it's again, it's you get the point. Okay, definition. If an integer a is a multiple of each of two or more integers, it is called a common multiple of these integers. The product of any set of integers is a common multiple of the set. The least integer, which is a multiple of each of two or more integers, is called the least common multiple. And it's evident that the integer 1 is a divisor of every integer, and that it is the only integer which has this property, hence it is called the unit. And next definition, two more definitions, two or more integers which have no common factor except one are said to be prime to each other or relatively prime. So for example, 14 and 15. 14 is not a prime number, 15 is not a prime number, but they're relatively prime because 14 and 15 do not share any common factors, other of course than one. That's trivial. That's one is that's a gimme. Okay, next definition. If a set of integers is such that no two of them have a common divisor besides one, they are said to be prime to each other. So same idea. Okay, well, I want to do some of these exercises. Let's listen to the first exercise. Prove. Whoops. Let's do. I want to do. I like to do with you now. Two of these. The first two of these problems. Show you how. What is that? Prove that n cubed minus n is divisible by 6 for every positive integer n. Okay, let's just get to that. So here's our problem. Prove that n to the third power minus n is divisible by 6 for every positive integer n. Well, let's check that out on a spreadsheet first, just get an idea what we're talking about, and then we'll see if we can prove it. So here's just 1 through n. These are different numbers. So I want my column B is going to equal n to the third, which is this number to the third power. Whoops. Oh, that's not good. Okay, minus the same number. So it's n cubed minus n. Let's see what we got here. So here we have 0. Well, 0, everything goes into 0. So this is a multiple of 6 because, it's good. And let's continue. Let's see what we got here. And 6, 24. Well, I can pretty much see these are all multiples of 6, but in case you're not convinced, let's divide them by 6. Let's let this equal to this divided by 6. I just want to make sure these are all whole numbers. And there you go. So column C is just that I took column B and divided everything by 6 just to show that I have no remainders or anything like that. So everything in column B, so column B is n to the third minus n. And when I divide each thing by 6, I get no remainder. So let's see now if we could prove that mathematically. And this is actually, I'm not even going to use induction here. I'm just going to use a very simple algebraic argument. And here we go. N to the third minus n. Well, let's factor it. Let's factor out the n. So that's n times n squared minus 1. Well, that's n times n plus 1 times n minus 1. If you notice, I have 3 consecutive integers, n minus 1, n, and n plus 1. These 3 numbers are all 3 numbers in a row. It's consecutive, 3 consecutive integers. Well, if you have 3 consecutive integers, at least one of them has to be an even number, right? You can't have 3 numbers in a row and none of them be even. At least one. Sometimes it could even be 2, but at least one has to be even. And and at least one has to be a multiple of 3. These are 3 numbers in a row. At least one of them has to be a multiple of 3. Well, I have an even number times a multiple of 3. It's all in there. That's 6. Wow, there's my proof. Now let's go back to the spreadsheet. That's interesting. Suppose I make another column of, instead of dividing by, instead of dividing by 6, I divide by 12. See what happens here. Now, if you notice, all of the odd ones are whole numbers. It's only the even ones which might not be. The reason is because when you have 3 consecutive numbers, half the time you're going to have one multiple of 2. Half the time you're going to have 2 multiples of 2. Now, sometimes you may have other things, a multiple of 4, other things like that. But the point is that I'll never see that if that's 1, 2, 3, 4, 5, 6. So I'll never get a fraction. So every time there's a fraction, it's always on an even. So it's 6 and 4 because these are times that I could just have one number's multiple of 2. But all these other ones, the odd ones, I would have more than one. Anyway, that's the counter side part. I'm going to discard this. We don't need it. I want to go on to the next problem. Again, I like to show you these things on the spreadsheet. Not that it's a proof, but it just gives you a sense of what's going on. Next, what's the next problem? If a product of 4 consecutive integers is increased by 1, the result is a square number. So I want to take the product of 4 consecutive integers and increase it by 1, and that will give me a square number. Okay, I'm going to show you how to do this again. I'm not going to bother with induction here. I'm just going to do a very simple algebraic argument. Okay, so let's see what this looks like. The product of 4 consecutive integers increased by 1, the result is a square number. So let's see what that looks like. The product of 4 consecutive integers, well, the 4 integers are going to be n plus 1, n plus 2, n plus 3. Those are 4 consecutive integers. Now, when I multiply that all together, if you just crunch this all out, you get n to the 4th plus 6n cubed plus 11n squared plus 6n. Now, what we want to do is add 1 to this. So if I add 1 to this, I'm going to add the 1. Well, guess what, folks? Oops. Guess what, folks? This is equal to a perfect square because this is equal to n squared give me 1 second. Let's see, this is n squared well, based on that 6, I'm gonna do half of 6 is 3. That makes sense if you know what I'm talking about. 3, and then based on the 1 that's plus 1. And let's square it. There you go. So this is equal to, so I took the 4 consecutive integers, multiplied them out, added 1, and that gives me n squared plus 3n plus 1 squared. And if you don't believe me, FOIL this whole thing out, multiply this whole thing out whichever way you want to multiply it, and you will get n squared plus 3n plus 1 squared. You'll get n to the 4th plus 6n cubed plus 11n squared plus 6n plus 1. Let's check this out on the old spreadsheet. Let's see what we get here. Let's do 4 consecutive integers. Okay. So we have, again, I always make my first column like this. Now this is going to be equal to Oh, I see it. Oh, oh. I forgot. You can't just do parentheses. You got to put these things. Okay, so here we have. That's A1 plus 2, and that's right. So 1 times 2 times 3 times 4 plus 1 is 25. And this is 2 times 3 times 4 times 5 is 121. These are all perfect squares. If you don't believe me, let's square root everything. I'm not sure if we have square root. Yep, and these are all so these were clearly perfect squares because when I square rooted them, I got whole numbers. And there you go. Anything special about these numbers here? I just see that they increased by 2. From from 5 to 11, it's a difference of 6. A difference of 8, 10, 12, 14, so forth. So that's the only thing. That's the only little pattern I'm noticing here. Anyway, there you go. We did that's 1.2, and we worked out some of the problems. Just I want to give you an idea of how to work these problems out. And that, my friend, is the story. We're done for this little fun little session. That's the end of this little video, and we'll continue next time with more exciting mathematics.